Okay. All right. So, review of stoichiometry. So I know that we're going to go into a little bit of overtime today, you guys. So if anybody has to leave, I will make sure that this is up ASAP on Canvas. So just by the by, I know some of you guys have other classes you need to go to. Okay, so review of stoichiometry. So the first thing that we're looking at here are molar conversions. And the other one is a balanced chemical equation, right? So we're combining these two things. So the molar conversions, just a little reminder, we got this thing called the molar coaster, which can help you visualize where you're trying to go when you're problem solving. So if we start out at grams, and we want to go to moles, what piece of information do we need?
Molar mass.
The molar mass, that's correct. So we need the molar mass to get us from grams to moles or moles to grams. Going from moles to atoms or molecules, right? We said what piece of information do we need?
The Avogadro's number.
Yeah, Avogadro's number, right? So I would say that this area of the molar coaster is something that we're going to kind of do away with, right? So if that was something that you were struggling with, you probably won't see it again unless we do, unless you want to do an exam review with me, right? But going into stoichiometry, we're usually concerned with going from grams to moles or back. The other thing that we're often concerned with is going from moles of one thing to moles of something else, right? So this is where we needed the molar ratio, right? And in our molar conversion problems, the molar ratio would often come from the chemical formula, right? So let's say we were going from moles of CH4 to moles of H, right? What would the molar ratio be?
4.
So for every one of these guys, right, we have 4 of these guys, right? So is everybody comfortable with that, kind of, sort of? Cool. I think the one area that these get a little confusing, which a lot of you guys saw on the exam, was when you're going from moles of, let's say, oops, sorry, something like this. I'm sorry. So the molar ratio, a lot of the times we're using the chemical. Thanks. We're using the chemical formula, right? So when we're going from moles of CH4, for example, to moles of hydrogen, our molar ratio comes from right here, right? For every one of these guys, I have 4 of these guys, right? Does that make sense, Alex? Sorry, I'm cool. Going between windows here. Okay, so I think the part that some of you guys got a little hung up on with the exam was something like this. If you're trying to go from moles of this molecule to, say, moles of oxygen, right? in this case, how do we do that?
You multiply the 2 times 2, so you get 4.
Yes.
So flipped against.
Right, so this 2 out here applies to every atom inside of the parentheses, right? So it's not just 2 of the oxygen, it's 2 times 2, right? Or 2 times 3, or 2 times 2, if we're talking about the carbon, right? So that molar ratio is a slightly more complicated version, but it's still using the chemical formula, right? So this would be 4 to 1 as well. Does that make sense, guys? Everybody okay with me? Cool. So that's one instance of the molar ratio. The one that we're going to work with for stoichiometry is looking at the coefficients from the balanced chemical equation. And what this does is it allows us to go from, let's say we have moles of reactant and we want to go to moles of product, right? Does that make sense, guys? So this is literally going from moles of one compound or molecule to moles of another compound or molecule, right? So here we were going from moles of molecule or compound to atoms, right? In this case, we'll be going from moles of reactant to moles of product, or we could even go from moles of one reactant to moles of another reactant, moles of one product to another product. Does that kind of make sense? I know I'm being kind of vague here. You guys all right with me? Questions? Cool. All right. So let's take a simple-ish equation. Oops. No, what am I doing? Let me try again. Right. So just as a brief reminder, what kind of reaction is this?
A combination.
Combination, yeah. Awesome. I love that.
And it's
Combo.
balanced.
Say again?
And it's balanced.
It is balanced, yeah. So I balance this for you. So that's the nice thing, at least about these, is a lot of the times when we're working with these stoichiometry problems, I don't want being able to balance to get in your way. So I would much prefer that you guys focus on how to do the problem than how to balance when you're doing stoichiometry. Does that make sense? So I'll always give you the balanced chemical equation for this. Coolsies. So let's say we have 50 milliliters of hydrogen gas and excess nitrogen gas. How much, how much ammonia we're thinking mass can be produced? Okay, so this is slightly more complicated than the ones that we've done before because it's incorporating our gas law stuff. So we will be going over this problem, we'll be going over gas law stuff and stoichiometry. Okay, so it's killing two birds with one stone. Okay, So before we get into how to solve the problem, let's just talk about what some of these key terms mean, right? So what does it mean to say that we have excess nitrogen gas?
Think about like the fish tacos. So we have one limiting factor and one excess factor.
Exactly. So which one is limiting?
The 50 milliliters of hydrogen gas.
Yes, the hydrogen gas. Alex, is it still blurry for you? Okay, so the question says we have 50 milliliters of hydrogen gas and excess nitrogen gas. How much ammonia can be produced? Okay, so we're looking at the mass of ammonia. Okay, yeah, no problem. Cool. So we know that H2 is our limiting reagent, right? And that's important because that means that we can use the amount of hydrogen gas that we're starting with to determine how much product we're making. Does that make sense, guys? Y'all good with me there? Cool. So in most of the problems that we've been starting with, we've had grams of a reactant to start. And here we have a volume, okay? So we're gonna assume that this reaction is happening at standard temperature and pressure. Did we talk about this? Standard temperature and pressure? I feel like we mentioned it. So the standard temperature is always going to be this, right? AKA 0 degrees Celsius. And the standard pressure is always going to be, anybody know? One atmosphere. Okay? You guys all with me here? So this STP would be given to you in the problem, right? So you would need to know these definitions. Okay, so that's definitely something that you should know. Standard temperature and pressure are 273.2 or 200 or just 273 degrees Kelvin and 1 atmosphere. Okay. So if we know the temperature, the pressure, and the volume, right? Thinking about our perv nert, right? Which variable are we missing here? Or can we solve for? So we have this, right? We have this. You guys with me?
The number?
R is the gas constant, right? So we always know that one.
We have that.
And we have this guy, right?
Yeah, we are looking for the number.
So what is this guy? The number...
It's in my notes somewhere. Number of moles.
It's the number of moles, right? Does that make sense? Yeah, absolutely, Kata. Everybody all right with me? Yeah? Cool. So if I want to solve for n, right? How do I get n by itself?
You gotta get rid of the R and the T, divide them out.
Mm-hmm. So I need to divide both sides by RT, right? So I'm going to get the moles of hydrogen gas will be equal to PV over RT. Does that make sense, guys? Now we just have to make sure that all of our units are correct. So reminder, R is equal to this, where our units are liters times atmospheres divided by moles times Kelvin. So our pressure is in atmospheres, our temperature is in Kelvin, but our volume is in
Milliliters.
So what do we need to do to get milliliters into liters?
Multiply it.
You guys remember these?
Is it 100?
Close.
1,000.
It's 1,000. Milli, right? Milli is 1,000. Like the millennials. You guys are the 1,000.
Like the millennials.
Yeah. So there's 1,000 milliliters for every 1 liter, right?
Yeah.
So that means that we have that many liters. You guys cool with me? Okay. So let's plug in all our variables here. So we have 1 ATM times 0.5 liters divided by 0.8206 liters atmospheres per mole Kelvin. I'm sorry, things are getting a little small. Times 273.2 Kelvin. Why is it H and not N? So it says N is in excess, Alex, because that's not the limiting reagent, right? So what that statement is telling you is that this guy we have more than enough of, right? We have extra. This guy is the one that's limiting how much product we can make, right? So this guy is the bottleneck. Does that make sense? So this guy is who's going to determine how much product we can make. So the first thing we're solving for is how many moles we started with of hydrogen gas, right? Once we know how many moles of hydrogen gas we started with, then we can use the stoichiometry to convert to moles of ammonia, right? Yeah, there's a lot of steps going on here, guys. I know, it's a lot. But we're learning. Yay! Jessica, what's up?
How did you know? I was gonna say something.
Because you got the look.
I figured it out. So the unit, though, when you get the answer, is just moles.
Yep, totes.
Okay, I sometimes confuse that with the molar mass because for a long time I didn't understand that it was grams over mole.
Yeah.
But I got it.
Yeah,
Okay.
cool. Yeah, that's super important, guys. So knowing that the units of a molar mass are grams per mole is super important, right? Yeah. That was a really good point, Jessica.
So I got 0.00223 moles.
Anybody want to back her up on that?
Notate it?
0.00223.
Is this an instance when we would want to do scientific notation because it's nicer?
You could, yeah. Anybody else get the same thing? Or are you guys just riding her wave? Steph is usually my backup, and her hand is sad. Okay, cool. Thanks, Ashley. Cool. Okay, so, and is everybody comfortable with how the units cancel out here? Yeah? Anybody uncomfortable with that? Cool. Awesome. So, this is how many moles of hydrogen gas we started off with. Now, we can go to the next page.
Professor, Alex asked to refresh, maybe on the units.
Oh, refresh on the units? Okay, so looking back here, we've got ATMs on the bottom and ATMs on top, right? Cancel, cancel. We got liters here and liters up top. Get them out of here, right? We've got Kelvin here and 1 over Kelvin here, right? This is 1 over Kelvin. So those guys cancel. So the units that you end up with are 1 over moles, right? Which you just take the reciprocal of this and multiply. So you do 1 times moles over 1, which is just moles. Cool, Alex? Cool. Awesome. Okay, so get a new clean page. I'm going to write our balanced chemical equation up at the top again. Oops. And we said we started with this many moles. Am I writing that down correctly, guys?
Yeah.
Cool. All right. So, just a reminder, what are we trying to find in this problem? What's our end game?
How much ammonium can be produced?
How much ammonia, not ammonium, right?
Oh.
But this is a really important point, right? Ammonium is this guy, right?
Yeah.
Right? This guy is ammonia. Just so you guys know. Sorry, I went off the page. Cool? Good thing to know. Cool. Okay, so we're looking for grams of ammonia, right? Everybody cool with me? Cool. I feel so bad that you're thumbs upping me right now, Steph.
I can't do anything else.
You're doing such a good job, though. It's such a good thumbs up for being not movable. Okay, so we have moles of H2, right? And we want to get to grams of NH3, right? Is there a direct path from moles of H2 to grams of NH3? Meaning a one-step process?
I would first do the molar ratio.
So I like where your head's at. So we're not going to be able to go straight here, right? We're going to need to take a step in between, right? Mm-hmm. So first thing we'll have to do is go from moles of hydrogen gas to moles of ammonia, right? Is everybody comfortable with that? Cool. We'll talk about how to do that in just a second. Then, once we have moles of ammonia, we want to go to grams of ammonia, right? This one you guys are familiar with, right? What do we need to do to go from moles of something to grams of something? Molar mass. Exactly. Everybody all right with that?
Yeah.
So, the question is, how do we get from moles of H2 gas to moles of ammonia gas, right? And that's where the balanced chemical equation comes in, right? So we know, based on our recipe, that we need 3 moles of H2 for every 2 moles of this guy, right? So we have 3 moles of H2 for every 2 moles of ammonia. Does that make sense? We cool? Cool. So this is the molar ratio from the balanced chemical equation, okay? Does that make sense, guys? Cool. All right, so we have the piece of information we need to make this step. Now we can solve for the molar mass of ammonia. 14.1 plus 1.008 times 3, 17 something. I'm just finding the molar mass of this guy.
17.03. So yeah, 17.
Word. Everybody all right with that?
Wait. Why is it not N2H6. Technically.
Oh, sorry for that face, you guys. So this stoichiometric coefficient, this is a really good question, you guys, okay? The stoichiometric coefficient belongs to the balanced chemical equation, aka the reaction or recipe that we're using, okay? The molar mass belongs to the compound, okay? So the molar mass of ammonia is not changed by having ammonia in different kinds of chemical reactions, right? So you could have, there's infinite different combinations of these reactants and products, right? But the molar mass, right, this guy belongs to the molecule. This is not trivial at all. Not the reaction, okay? So this is super, super, super important, right? This is the number one thing that I see students doing wrong with stoichiometry problems, is they want to take the molar mass and multiply it by this coefficient, right? Do not do that, okay? Molar mass belongs to the molecule, not the reaction. Okay? Great question. Any other questions so far? This is so good, you guys. We're making such good progress. Okay. So, now, looking at my dimensional analysis, right? What unit do I want on the bottom?
Moles of H2.
I always want to cancel out the thing that's on top over here, right? So I'm always going to want to put that same unit down here. And what unit am I trying to get to?
The moles of the whole compound.
Moles of ammonia, exactly.
Productory.
Of the product, yes. That was good. I like that. Okay, so now what are the coefficients that go on top and bottom?
It's 2 to 3, right?
Where's the 2 go?
2 on top, 3 on bottom.
So I have 2 of these guys for every 3 of these guys. Is everybody comfortable with that? Questions? Cool. So then this guy cancels with this guy, right? And now what's the unit I want on bottom here?
Moles of NH3.
Yeah. And what do I want on top?
Grams.
Yeah. Right? So for every one of these guys, right? One of these guys, I have 17.03 of these guys. So now moles of this guy cancel with moles of this guy. Is everybody comfortable with how we did that? It's a lot, right? It's a lot. But
It's a lot of steps.
It's a lot of steps, but I really think that if you do this kind of visualization for each problem, it's super helpful, right? I know that I kind of filled in a lot of the gaps here, but if you can do this kind of roadmap, right, then figuring out what components you need becomes a little bit easier, right? Because going from moles to moles of something, right, we're always thinking we need a molar ratio. Going from moles of grams, moles to grams, we're thinking molar mass, right? So this is just kind of making an extended version of our molar coaster, right? So, what do we get?
I got 0.0253 grams.
0.0253 grams.
Mm-hmm.
Everybody all right with that?
Dope.
Yeah. So one of the reasons why I wanted to do a gas problem was, again, to kind of review how to do gas problems. but also because I wanted you to see that all of the problems that we'll be doing going forward can have the possibility of being stoichiometry problems, right? So this was a gas stoichiometry problem. The next chapter that we're going into, solutions, will be all about solutions and solution stoichiometry, right? So I know. So that's why this concept of stoichiometry is really, really important, and I wanted to make sure that you guys have enough time to digest it, right? Because it's not going to go away. So, have more videos on this type of problem. Not on this type, but like you mean like a gas stoichiometry problem or stoichiometry in general, Kata? This particular kind? I don't know, but there will be more of these in the homework, right? So I apologize, I don't have the homework up yet, but I will have that up ASAP, and then you'll be able to practice these kinds of problems, right?
I was gonna there's con videos on YouTube about stoichiometry. Those helped me a ton.
Yeah, Khan Academy is a really good resource. So KHAN Academy.org, right? They go through a lot of different types of problems, and they have like a ridiculous amount of videos. Yeah. Yes, I apologize, guys. Sorry, real quick, Najma. I'll get back to you. I apologize, you guys. I kind of stopped posting external links because it takes me so much time to go through them and like evaluate. But if you guys have those kinds of things to share with each other, please, please, please put them into discussion forums, right? So if you guys are utilizing, a particular, I know Kata was utilizing, have you guys seen Maribella, I think is her name. So she's another really common one that does videos. So yeah, Melissa Maribel, yeah. So there's a lot of these like Chem tutor people on YouTube, and they have some really good content. I would say that for your guys' level, though, Khan Academy is probably one of the best, right? And you can actually download the app on your phone, so I guess it doesn't really matter, but well, like you guys aren't really going many places these days besides work, I'm guessing, so, but I don't know, some of you guys are still working, on your break. Maybe you could be studying chemistry because that's totally the thing you want to do on your break at work, right? Yeah, anyways. I'm sorry, Steph. She's like, no, thank you. Cool. Yeah, no worries. Sorry, Najma, go ahead.
I just want to ask for the quiz this week on stoichiometry. Will it be like more like this, a gas problem, or is it just going to be like completely different?
I'm probably not going to combine those two things, right? So it'll probably be more starting off with grams of something, right? Instead of starting off with a volume of gas, because this is kind of a 1-2, right? But you will, as we progress in this material, the gas quiz could have something like that, or the next exam, that kind of thing. Does that kind of make sense?
Yes, thank you.
Cool. Yeah. Any other questions about this one?